At the height of Second World War, the Nazis made 664 uranium cubes.
The case of the missing uranium cubes from Nazi Germany's unsuccessful reactor. In 1945, Nazi scientists were trying to manufacture.
Now they're quietly resurfacing, and scientists are worried. These unassuming blocks were at the heart of Hitler's ill-fated ambition to develop an atomic reactor. This project never came to fruition, but left behind a legacy both eerie and unsettling. Decades later, the mystery of these cubes remains unsolved, as hundreds of them, once secured by Allied forces, have vanished from official records. Today, as scattered remnants of this dark chapter resurface in surprising places, from university collections to garage sales, there is reason for concern. One has to wonder, where are the missing cubes? And could they pose a modern danger? Well, that's what we're going to find out. The Nazi nuclear program. During the Second World War, amid the relentless pursuit of technological and military supremacy, Nazi Germany embarked on an ambitious yet ultimately futile quest to develop nuclear energy. However, unlike the successful Manhattan Project, the Nazi nuclear program was marred by scientific flaws, political obstacles, and organizational chaos. This tragic combination of factors not only stalled Germany's progress, but also left behind a legacy that continues to provoke curiosity and concern. In the late 1930s, as Europe edged closer to war, German physicists were at the forefront of nuclear research. The discovery of nuclear fission in December 1938 by German chemists Otto Hahn and Fritz Strassmann, with theoretical explanations by Lise Meitner and Otto Robert Frisch, marked a scientific breakthrough that could have changed the course of history. This ushered in the nuclear age. And ever since, the human race has lived under the threat of a nuclear holocaust. Following Hahn and Strassmann's discovery, physicist Werner Heisenberg, a Nobel laureate and key figure in Germany's nuclear program, recognized the military potential of nuclear fission. In early 1939, Heisenberg presented his ideas to the German Army Ordnance, suggesting the feasibility of building a uranium-based reactor. He speculated that such a reactor could generate enough plutonium for a bomb. In response, the German government established the Uranverein, or Uranium Club, in September 1939, mere days after the invasion of Poland, to expedite nuclear research. The Uranverein was a loosely connected network of scientists and institutions tasked with developing nuclear energy for military purposes. The program included prestigious scientists such as Heisenberg, Kurt Diebner, and Carl Friedrich von Weizsäcker. These experts, many of whom were prominent physicists from German universities, worked in various research facilities, including the Kaiser Wilhelm Institute for Physics in Berlin and the University of Leipzig. Despite the apparent intellectual firepower, the Uranverein was plagued from the outset by inefficiency and lack of coordination. Unlike the centralized and well-funded Manhattan Project, the Nazi program lacked consistent leadership and a clear vision. Political interference and ideological biases further hampered progress. Notably, many capable Jewish physicists had been forced to flee Germany, depriving the program of valuable expertise. One of the most critical setbacks for the Nazi nuclear effort was the fragmented structure of the program. Rather than operating as a unified project, the research was divided among different military branches and academic institutions, each guarding its discoveries and methods. Kurt Diebner, a physicist with close ties to the German military, managed a separate line of research, often at odds with Heisenberg's academic approach. This rivalry created conflicting methodologies and a lack of synergy. Political interference was also a persistent issue. Adolf Hitler and his inner circle showed limited understanding of nuclear physics and prioritized immediate military needs over long-term projects. While Hitler dreamed of Wunderwaffen or wonder weapons to secure German victory, the nuclear program was sidelined in favor of conventional weapons development. Heinrich Himmler and the SS expressed sporadic interest, but this involvement often disrupted rather than advanced scientific progress. While organizational issues hindered the program's efficiency, fundamental scientific miscalculations further doomed it. A key problem was the Nazi scientists' flawed understanding of reactor design. Early experiments revealed that achieving a controlled chain reaction was more complex than initially thought. The German scientists decided to pursue a heavy water reactor design, believing that heavy water or deuterium oxide could act as a more effective neutron moderator than graphite. However, they lacked sufficient heavy water to scale their experiments. Heavy water was primarily produced at the Norsk hydro plant in Vemork, Norway. In a critical blow to the German program, Norwegian resistance fighters, aided by British forces, carried out sabotage missions in 1943 and 1944, severely limiting German access to this essential component. Moreover, German physicists grossly underestimated the amount of uranium needed to sustain a chain reaction. They incorrectly calculated that a reactor could function with significantly less uranium than was realistically required. These theoretical errors led to failed experiments, including Heisenberg's famous attempt at building a reactor at Haigerloch in 1944. This experimental reactor, designed with 664 uranium cubes suspended in a lattice structure, never achieved criticality, as the uranium density and moderator configuration were insufficient. By 1944, it became evident that Germany was losing the war, and resources for scientific research dwindled. In contrast, the United States, fueled by fears that Germany might succeed in building an atomic bomb, had already accelerated the Manhattan Project. The Uranverein, however, remained fragmented and poorly coordinated. While American scientists worked around the clock with unlimited resources, Heisenberg and his colleagues were debating theoretical possibilities and constructing ineffective reactor designs. The lack of urgency was partly rooted in Heisenberg's own ethical reservations. Some historians suggest that Heisenberg deliberately slowed progress, believing that a Nazi atomic bomb would be morally catastrophic. In the end, Nazi Germany never came close to achieving a functional nuclear reactor, let alone a bomb. So, what was the deal with those radioactive cubes? The Nazi uranium cubes. As part of their efforts, Nazi scientists devised a plan to build a reactor using uranium cubes as the primary fuel source. Each cube measured roughly 5 centimeters, or about 2 inches on each side, and weighed around 2.5 kilograms, or 5.5 pounds. Composed of natural uranium, these cubes were fabricated to serve as the core components of a nuclear reactor, suspended within a lattice structure. In total, 664 of these cubes were produced. The envisioned reactor was designed to be a self-sustaining nuclear fission system. In theory, when configured correctly, the uranium atoms in the cubes would undergo fission, releasing neutrons that would strike adjacent atoms, triggering a continuous chain reaction. To moderate this reaction and sustain it efficiently, the German scientists chose heavy water or deuterium oxide as the neutron moderator. This choice was based on the belief that heavy water would slow down neutrons more effectively than graphite, thus maintaining the chain reaction. The Nazis conducted a series of experiments to create a functioning nuclear reactor, with key facilities located in Leipzig, Berlin, and later in a subterranean cavern in Haigerloch, southwest Germany. The Haigerloch reactor, constructed in 1944, became the most significant attempt at achieving a chain reaction. The setup included a spherical tank filled with heavy water, within which the uranium cubes were suspended on a frame. Despite the meticulous planning, the reactor experiments faced fundamental scientific challenges. One major flaw lay in the cube arrangement and density. The uranium was not densely packed enough to achieve criticality, and the heavy water, already in short supply, was insufficient for the reactor's needs. Furthermore, the German scientists grossly underestimated the amount of uranium required to sustain a self-sustaining reaction. Instead of forming a critical mass, the reactor remained subcritical, and no sustained chain reaction was achieved. Compounding these issues was the scarcity of heavy water. The only significant production facility was the Norsk hydro plant in Vemork, Norway, which fell under German control after the invasion of Norway in 1940. In a series of daring sabotage missions in 1943 and 1944, Norwegian resistance fighters, with British support, destroyed the plant's production capabilities, severely limiting the German nuclear program's progress. As the Allies closed in on Germany in early 1945, the race to secure Nazi scientific assets intensified. Ironically, while the Nazi regime failed to grasp the potential of nuclear weapons, the Allies feared that Germany might succeed. This fear spurred the Manhattan Project, leading to the rapid development of atomic bombs in the United States. In contrast, German scientists remained bogged down by theoretical debates and rivalries, never reaching the necessary breakthrough. Today, the uranium cubes are enigmatic relics of a failed scientific quest. A few cubes are displayed in museums, like those at the University of Maryland and Pacific Northwest National Laboratory. These artifacts serve as stark reminders of how scientific ambition, when entangled with ideological extremism and poor strategic planning, can lead to failure despite significant potential. Modern researchers continue to study the surviving cubes to verify their origins. Analysis of isotopic compositions confirms their authenticity as part of the Nazi nuclear effort. Yet, the fate of the majority remains unclear. But wait, didn't the Allies capture them all? So how come some of them are missing? Well, there's a whole story about that too. The Allied seizure and the post-war journey of uranium cubes. In early 1945, as Allied forces advanced into Germany, the United States initiated a covert operation known as the ALSOS mission. Directed by Colonel Boris Pash, this mission aimed to capture key German scientific personnel, research documents, and materials related to nuclear energy before the Soviets could seize them. The operation was motivated by the fear that Nazi Germany might be close to developing an atomic bomb, or that the Soviets could exploit German advancements. One of the most crucial discoveries of the ALSOS mission occurred in April 1945, when US troops reached the small town of Haigerloch in southwestern Germany. Hidden in a cave beneath the town's medieval church lay the remnants of Germany's most advanced nuclear reactor experiment, supervised by Heisenberg. Upon raiding the site, the ALSOS team discovered the aforementioned 664 uranium cubes. These cubes, crucial for the reactor's fission process, were hastily dismantled, packed, and shipped to the United States for analysis. The ALSOS mission successfully thwarted any remaining German nuclear ambitions and prevented the reactor materials from falling into Soviet hands. Once shipped to the United States, the uranium cubes were distributed among several research facilities, including the Manhattan Project sites at Oak Ridge, Tennessee, and Los Alamos, New Mexico. Scientists were keen to understand the structure, purity, and engineering methods used by the German nuclear program. Initial tests confirmed that the cubes were composed of natural uranium, with impurities that reflected the primitive metallurgical techniques available in wartime Germany. American scientists, including those working under J. Robert Oppenheimer, closely examined the cube's geometric configuration and density. The Germans had arranged the cubes in a loose lattice structure within the reactor, believing this would maximize the neutron flow necessary for sustaining a chain reaction. However, American researchers quickly noted that the reactor's design lacked the critical mass required for self-sustaining fission, primarily due to the poor arrangement and inadequate amounts of heavy water. Beyond scientific analysis, some of the cubes were repurposed for the US nuclear program, particularly for tests related to reactor designs and the enrichment of uranium. However, their limited quantity and the fact that they were composed of natural uranium rather than enriched uranium made them less suitable for direct use in atomic weapon production. Despite their initial scientific value, the uranium cubes soon became victims of bureaucratic neglect and haphazard distribution. By the late 1940s, the urgency of examining the cubes had faded as American nuclear capabilities advanced. The lack of a formal inventory system or dedicated oversight led to the cubes being scattered among various government laboratories, universities, and even private individuals. While some of the cubes remained in the custody of national laboratories, others were gifted to scientists involved in wartime research as mementos. In some cases, military personnel took them as souvenirs without official documentation. Over time, the official count of the uranium cubes dwindled, and many simply disappeared from the records. Reports surfaced throughout the following decades of uranium cubes appearing in unexpected places. In the 1970s, a cube was discovered at the University of Maryland, tucked away in a dusty storage room. In 2013, another cube was found at the Pacific Northwest National Laboratory, where it had been miscatalogued for decades. Both were verified as part of the original haul from Haigerloch. Further complicating the trail, some cubes made their way into private collections. One such cube was acquired at a garage sale in the 1990s, while another was displayed in a local history museum without clear documentation. Of the 664 uranium cubes originally seized by the ALSOS mission, fewer than 20 have been conclusively identified and accounted for in modern times. This leaves roughly 600 cubes unaccounted for, raising questions about their fate and current location. Given that uranium remains a controlled substance, the potential presence of these cubes in private hands presents both legal and environmental concerns. Some historians suggest that the cubes were simply misplaced within the labyrinthine bureaucracy of post-war scientific research. Others believe that some may have been scrapped or lost during transfers between research facilities. Notably, in 2021, researchers from the University of Maryland conducted a study on one of the identified cubes, attempting to trace its origins through isotopic analysis. The study aimed to match the cube's unique uranium signature to known German production methods, confirming its authenticity as part of the Nazi nuclear effort. Such studies are ongoing, but the lack of clear records from the immediate post-war period hinders the search. One intriguing theory suggests that some cubes may have been deliberately hidden or discarded by individuals who either feared legal repercussions or simply did not comprehend their historical value. There is also the possibility that some cubes were traded or sold through informal channels, given the chaotic aftermath of the war and the widespread distribution of scientific memorabilia. Today, the surviving uranium cubes serve as physical reminders of a failed nuclear ambition. As historical artifacts, they encapsulate the intersection of scientific ingenuity, ideological extremism, and wartime desperation. Museums and laboratories that possess the few known cubes treat them as both educational tools and cautionary tales. Interest in the cubes has been rekindled in recent years, particularly among historians and nuclear physicists who seek to understand how close the Nazis truly came to achieving atomic power. As part of ongoing research, isotopic profiling and metallurgical analyses continue to shed light on the technological limitations of the Nazi nuclear program. The story of the uranium cubes is a stark reminder of how scientific progress, when driven by ideological zeal and fractured leadership, can lead to unexpected outcomes. The Allies' seizure of the cubes not only halted a potential German breakthrough, but also highlighted the strategic importance of scientific intelligence in warfare. However, the mystery of the missing cubes, the secrecy that shrouded their initial seizure, and their gradual reappearance in unexpected locations reflect the unpredictable aftermath of wartime innovation. This is a bigger deal than it sounds. Modern investigations into the missing uranium cubes. While only a handful of these cubes have been positively identified, many remain unaccounted for, leading to modern efforts to trace and verify their authenticity. The journey of modern investigations into the uranium cubes began in 2013, when Timothy Koath, a physicist and historian at the University of Maryland, unexpectedly received a peculiar package. The package contained a small, dense cube of uranium, approximately 5 centimeters per side, accompanied by a cryptic note, taken from the reactor that Hitler tried to build. Gift of Ninninger. This note intrigued Kurth, sparking an investigation that would last for years. Kurth soon partnered with Miriam Hebert, a materials scientist specializing in historical nuclear artifacts. Together, they aimed to verify whether this cube was one of the original 606-4 uranium blocks seized by the Allies from the Haigerloch reactor. Their first step was to conduct scientific testing to authenticate the cube's origins. Koeth and Hebert used radioisotope testing and gamma spectroscopy to determine the cube's composition and radioactive decay profile. Natural uranium primarily consists of isotopes uranium-238 and uranium-235. By analyzing the cube's isotopic ratios and decay signatures, they confirmed that it was composed of natural uranium, just as expected from wartime German production. Gamma spectroscopy revealed a distinct signature associated with uranium that had not been subjected to modern enrichment processes. This was significant, as the Nazis lacked the technology to significantly enrich uranium, relying instead on naturally occurring isotopes. Furthermore, the cube bore physical signs of primitive metallurgical techniques, such as rough edges and uneven casting, consistent with known Nazi methods. To bolster their findings, Koeth and Hebert collaborated with several national laboratories and museums, including the Pacific Northwest National Laboratory and the Smithsonian Institution. These institutions provided access to reference data from other known uranium cubes, helping the researchers cross-verify the cube's characteristics. The consistent findings across these examinations strengthened the hypothesis that Keth's cube was indeed part of the original German cache. Despite the successful verification of this particular cube, Keth and Hebert soon realized that their task was far from complete. One of the major challenges they faced was distinguishing authentic uranium cubes from potential counterfeits. As the cubes had passed through numerous hands over the decades, some were incorrectly labeled or misrepresented as authentic. One problem lay in the lack of documentation. The original list of seized uranium cubes from 1945 was incomplete, and records of their subsequent distribution were even more fragmented. To ensure authenticity, Koeth and Hebert developed a set of criteria based on physical properties, isotopic analysis, and provenance research. For starters, they expected the authentic cubes to have the natural uranium signature from the 1940s. Moreover, many cubes bore drilled holes or scratches consistent with being suspended in the Haigerloch reactor's lattice structure. Then there were provenance records, notes, or accompanying documentation that linked the cube to known storage sites. To their surprise, some cubes circulating among collectors turned out to be fakes, either replicas made for educational purposes or unrelated pieces of uranium from later nuclear projects. One such case involved a cube found at a private auction, which, upon examination, contained traces of post-war enrichment, disproving its alleged origin. Koeth and Hebert's research also involved tracking the journey of the cubes from wartime Germany to their modern locations. They scoured government archives, military records, and personal correspondences. One critical discovery was a letter from the 1950s indicating that several cubes had been shipped to universities for research purposes, often without adequate records. Their investigation revealed that after the initial seizure, some cubes were sent to national laboratories for scientific study. Others were gifted to scientists or officials as souvenirs, sometimes accompanied by handwritten notes or certificates. However, as decades passed and interest waned, many of these cubes were misplaced, forgotten, or dispersed through unofficial channels. One of the most surprising discoveries occurred when a cube, thought lost for decades, was found in a laboratory drawer at the University of Maryland. It had been catalogued as a generic uranium sample, with its historical value entirely overlooked. This case showed how institutional negligence and the lack of systematic inventory had contributed to the cube's mysterious disappearances. Koeth and Hibert's research culminated in several scholarly publications and public presentations aimed at raising awareness about the scattered uranium cubes. In a 2019 paper published in Physics Today, they detailed the scientific methods used to verify the cubes and the historical context of their dispersal. The paper also highlighted the challenges of distinguishing authentic cubes from replicas, emphasizing the need for standardized preservation practices. One of their primary concerns was the potential risk posed by these lost uranium cubes. Although the cubes are not highly radioactive, they still emit alpha particles and can pose a health risk if handled improperly. Koeth and Hebert warned that private collectors, often unaware of the risks, might keep these cubes in unsafe conditions. Public interest in their work grew, leading to a feature on the National Public Radio, or NPR, and coverage by major science journals. The researchers used these platforms to call for a more comprehensive effort to locate the missing cubes. They advocated for creating a centralized registry where institutions and collectors could report discovered cubes and their current condition. One of the major takeaways from their investigation was the legal ambiguity surrounding the ownership of these cubes. Because uranium is a regulated material, possessing it without proper licensing could violate US federal law. Additionally, some of the cubes might have deteriorated over the decades, posing not just radiological but also chemical hazards. Koeth and Hebert urged collectors and museums to come forward and share information about the cubes in their possession. They emphasized that resolving the mystery of the missing cubes was not merely an academic exercise, but a matter of public safety. In response, several institutions that had previously concealed their cubes out of fear of legal consequences began to cooperate. While Koeth and Hebert's efforts have successfully identified and authenticated several uranium cubes, hundreds still remain missing. The whereabouts of these lost artifacts continue to intrigue historians and scientists alike. Some speculate that the cubes may still be hidden in forgotten storage rooms of research facilities, while others may lie in private collections, their owners oblivious to their historical significance. One lingering question is whether any of the missing cubes ended up outside the United States, potentially in the hands of collectors abroad. Given the historical context and the secrecy of wartime operations, the possibility of international dispersion cannot be ruled out. While Koeth and Hebert's meticulous research has brought some clarity to this complex puzzle, the final resolution remains elusive. As modern science continues to intersect with history, the uranium cubes serve not only as relics of a failed nuclear program, but also as symbols of the persistent quest for knowledge, even when that knowledge leads to uncomfortable truths. So, how risky are these cubes? Risks and concerns in the modern context. The legacy of Nazi Germany's failed nuclear ambitions is not merely a chapter in history, but a persistent challenge that continues to resonate today. The uranium cubes, once intended to power a Nazi nuclear reactor, are scattered around the globe, many of them still unaccounted for. At first glance, the uranium cubes may seem like inert historical artifacts. However, their potential threat becomes evident when we understand the nature of natural uranium and its role in nuclear technology. Unlike enriched uranium or plutonium, natural uranium primarily contains the isotope uranium-238, with only about 0.7% of the more fissile uranium-235. While not weapon-grade in its raw form, natural uranium can still be hazardous and exploited for nefarious purposes. Natural uranium itself is not immediately suitable for constructing a nuclear bomb, as its uranium-235 content is too low to sustain a rapid chain reaction. In contrast, enriched uranium, typically used in nuclear weapons, contains about 90% uranium-235, while plutonium, like plutonium-239, is also highly fissile and suited for weapons. The Nazi uranium cubes, being composed of natural uranium, could not have powered a conventional atomic bomb without extensive enrichment. Thankfully, Germany lacked the means to enrich uranium during the war. However, the danger does not solely lie in direct weaponization. One of the most pressing concerns is the potential use of these cubes in so-called dirty bombs. A dirty bomb, or radiological dispersal device, shortened as RDD, combines conventional explosives with radioactive material. Though it would not trigger a nuclear explosion, it could disperse radioactive particles over a wide area, causing contamination and public panic. The uranium itself would not cause mass casualties from radiation poisoning, but the societal and economic disruption could be profound. In 2003, US officials expressed concern that terrorist organizations might seek out radioactive materials for such purposes. This means that the scattered Nazi uranium cubes represent a legitimate security risk. Their relatively low radioactivity makes them harder to detect, allowing them to be trafficked or stored without arousing suspicion. This makes the missing cubes a real threat. On one hand, the radioactive nature of the cubes, while relatively mild, can still pose health risks if handled improperly. On the other hand, their potential use in dirty bombs or other unconventional applications represents a national security threat. Apart from security threats, improper handling of the uranium cubes could lead to contamination. Natural uranium emits alpha radiation, which, though not penetrating, can cause significant damage if ingested or inhaled. If one of these cubes were to be melted down or repurposed without safety protocols, it could lead to hazardous exposure. This issue becomes more concerning when considering the proliferation of the cubes during the Cold War. Some were distributed to universities and private collectors without strict regulation, making their subsequent tracking nearly impossible. In recent years, increased awareness has led some institutions to reassess their collections, but a complete inventory remains elusive. The intense rivalry between the Axis and Allied powers during the Second World War created a race for nuclear supremacy. This also directly influenced the post-war geopolitical landscape. When the Allies discovered Nazi Germany's nuclear efforts, the sheer scope of the project, though fundamentally flawed, alarmed scientists and military leaders alike. The fear that Hitler might acquire nuclear capability significantly influenced the urgency behind the Manhattan Project. By 1942, Allied intelligence indicated that Germany had made significant progress toward nuclear energy, including the development of uranium enrichment techniques. Although the German project was plagued by disorganization and scientific disagreements, the mere possibility of a Nazi bomb pushed the Allies to accelerate their own atomic research. This sense of urgency culminated in the successful test of the first atomic bomb at Alamogordo, New Mexico, in July 1945. Ironically, while the Allies were making groundbreaking progress, the Nazi nuclear effort remained stuck due to a lack of resources and technical missteps. After the war, the seizure of the uranium cubes provided tangible proof of the flawed German project. Nonetheless, the threat continued to shape post-war nuclear policies. The Cold War further complicated the legacy of the Nazi cubes. The United States, having secured these radioactive relics, became the world's leading nuclear power. In a twist of fate, the same scientific drive that pushed Nazi Germany to experiment with uranium would later enable the Allies to establish a nuclear monopoly. Despite being relics of a bygone era, the Nazi uranium cubes continue to captivate both historians and security experts. As long as these radioactive artifacts remain unaccounted for, they represent a potential hazard that cannot be ignored. There is an ongoing need to monitor and secure radioactive materials worldwide. With advancements in detection technology, scientists are better equipped to identify uranium samples, even those long thought lost. The challenge lies not only in locating the cubes, but also in balancing historical preservation with modern security concerns. Some historians argue that the cubes should be preserved as museum artifacts, while security experts advocate for their secure storage to prevent potential misuse. Finding a middle ground requires clear legal guidelines and cooperation between government agencies, museums, and private collectors. Recapturing these artifacts is not just an academic endeavor. It is a critical component of ensuring public safety and preventing the misuse of radioactive materials. As history has shown, the quest for nuclear power is fraught with ethical and security dilemmas. The story of the uranium cubes shows us how the ambitions of the past continue to shape our modern world, compelling us to remain vigilant for our own safety. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.